Okay. I hope you can see my slides. Can you?
Yes, sir.
Excellent. So, in last two classes, what we have been discussing was around earthquake seismology. And if you remember, we have said that seismology basically are studied in two branches. One is, of course, earthquake seismology, where the source is natural and where we study ins and outs about earthquakes. Uh, the other type of methods by which seismic is studied is called exploration seismology. And in case of exploration seismology, what happens is the source is not anymore natural. So you create some sort of elastic collision, you create some sort of vibration on the ground, and then you try to measure that vibration through geophones or detectors, if we use layman's language, detectors in other areas, and then you try to come up with the image of the subsurface. So it is the technique by which you create an acoustic image of the subsurface. It's very similar to the ultrasound as we have discussed. So similar to ultrasound because you cannot see inside our body. Similarly, you cannot see inside the earth. So you want to image it still. So you want to create those acoustic images by shooting seismic and then recording the reflected or refracted rays through those detectors. Okay, so essentially, this whole seismic method can be subdivided into few categories. So the first thing is what we call as seismic acquisition. As acquisition means, as the name suggests, it is the time when the seismic data is received from the earth. So you kind of shoot the seismic and then you acquire the seismic. That whole process is called seismic acquisition. And once you get the data needs to go through a series of processing. Processing means that you cannot simply use the raw data for the interpretation purpose. You cannot simply, the subsurface image is not clear from the raw data. So the raw data has to go through certain processes before you can actually make sense of that data. Okay. And then the final step is called seismic interpretation, where you are given a seismic section, yeah, and you are supposed to make a geological picture out of it. Okay, so for example, the first picture you can see here, the seismic acquisition is going on in the sea. Okay, so what you will observe that there is a boat, some trails behind this boat. Okay, so these trails are like attached to this boat. In this particular boat, there is some sort of sound wave is being generated, and these trails are attached with some sort of microphones. I mean, they are called geophones, but they are nothing but receiving or detectors. Okay, so what happens? This sound wave that you generate in this boat, okay, that kind of penetrates through the earth, okay, and gets reflected at different interfaces of layers, okay, and get refracted back or reflected back, okay. And when it is reflected back, they are essentially detected by these geophones, and then the data is recorded. Okay, this is the whole seismic acquisition process. Here, the example is given for ocean. So the similar thing is also done on the earth, on the continent. Okay, and then, of course, the data that you receive, that raw data, is then processed with several techniques which we will discuss. And then finally, the processed image can look something like this, okay, where you can make your geological interpretation. Okay, so here you can see. So this is a seismic map, and this is the seismic section. So in the seismic map, you can see the beautiful disposition of faults, how the faults are interpreted. You can see here also some faults, some different layers are interpreted. Okay, so this is the whole process in seismic. Okay, and let me tell you, although seismic is used in many different industries, but the most important industry where seismic is used is actually oil and gas industry, oil and natural gas industry. For example, ONGC, for example, Shell, ExxonMobil, and all these big companies where seismic technique is used. Okay, and there is a good demand for geophysicists work on the seismic data. So what essentially happens, where does this seismic acquisition and processing takes place in the whole exploration workflow? So exploration means you are going to a particular region and you are trying to explore whether that region is having enough oil and gas. And then you can drill that area out and then take the oil and gas out and then sell it, of course, after some process of the crude oil. Okay. This is how the whole process goes. And in this whole workflow, I will try to explain where this whole seismic acquisition and processing and interpretation actually sits. So first you identify opportunities. Say, for example, with your geological knowledge, someone told you, the company thought that Bhopal is an area of interest. Okay, so Bhopal is an opportunity. So, and how you have identified the opportunity? This is generally done by your understanding of the geological knowledge of that area. Okay, so all sorts of rocks do not produce oil and gas. Maybe later on you take the course of geology of wells, where I will be able to teach you how what are the different types of rocks where oil and gas actually sits. But for the time being, remember that all do not generally contain oil and gas. So your geological knowledge is extremely important in identifying opportunities. That you say that this particular place, for example, Bhopal, you say that is an opportunity because I know from my geological background knowledge that perhaps oil and gas could be here. And then you capture prime areas. Say, for example, you cannot do the operation everywhere. Suppose if the area is highly infested with people, say, for example, maybe MP Nagar of Bhopal, maybe that is not the ideal area where you will be able to do your business or do your drilling or acquisition. You need to find a calm and quiet area, where you are not disturbing the habitat a lot. Say, for example, Pori may be an ideal area where there are not many constructions going on and everything. Okay, so you find out some prime areas. Okay, and then acquire seismic data, and that is where you kind of make some blasts. Okay, and then put some detectors, and by which you acquire the seismic data. And then you process the seismic data, and then you interpret the seismic data. So once you interpret the seismic data, you have a fairly good knowledge about the picture of the subsurface, how the subsurface is looking like. Okay, and then you assess, prospect, how there are a few things you can do from the seismic image itself, together with something called well logs, and we will talk about well logs in the next class, perhaps tomorrow. Okay, you can actually say that whether this particular area is having oil or gas or not. You can also say if there is oil and gas, whether that oil and gas is how much oil and gas is there. Okay, so the first thing is whether there is oil and gas, and second thing is you have to say that how much oil or gas is there. And then you do some economic analysis. Economic analysis means, say, for example, I'll give you some numbers. Say, for example, if you want to drill a well in Gulf of Mexico, it costs almost like $20 million. Okay, one well costs $20 million. Well means a small hole that you drill inside the ground. Okay, a small hole like tube oil. Okay, so how tube oils? Why tube oils are put? Tube oils are put to take out water, the groundwater, right? Similarly, if you want to take out oil and gas, you have to drill wells, okay? And the wells are way more sophisticated than a tube well, okay? And such wells, maybe in Gulf of Mexico, costs around $20 million, one well, okay? And maybe for an area of 20 square kilometer, you need around 20 wells, yeah, roughly speaking. So you can imagine how much investment. So it's $1 billion business, right? So how much investment do you make to actually get out oil and gas from an area? Okay. Now suppose the oil and gas you take out is not, when you sell them, is not profitable enough. That means that whatever oil, there is oil and gas, but then the oil and gas that that you sell is not giving you profit. So whether would you drill a well there? Perhaps not, simply because the oil and gas is not uh, attractive enough to go ahead with the opportunity. Okay, so if you do an economic analysis and if it says yes, it makes sense to actually drill there, you drill the first well in that area, and that is what we call an wildcat drilling. Okay, wildcat means that is completely a virgin area. You have no idea whether oil and gas is there. I mean, you have some idea from the seismic, but you have not actually ground truth to your understanding. So you drill your first well, and the first well could be a success or could be a failure. Success means that you hit the oil and gas, okay? And then or you don't actually hit oil and gas. The well becomes dry. It doesn't produce any oil and gas. Okay. So, and then if it is a success, then you drill further wells, of course, and then you take that particular field to development. That means you drill number of wells to take the oil and gas out. And if it is a failure, of course, then there are other processes that goes on. Maybe you drill further few more wells and see if it is actually true that there is no oil and gas there, or the oil and gas is low enough to actually make it economic. If it happens that it is not economic, then you drop that prospect. You say that I am going out of Bhopal. I don't want to invest my money in this area. Okay. So in this whole exploration workflow, at the very early stage, the seismic acquisition, processing, and interpretation comes. Is that clear, guys? Anything you did not understand? Because this is all very new to you. You have to tell me if it is clear. Excellent. So this is how seismic is shot, and I'll tell you how it happens. So suppose this is when we were talking about earthquake seismology, the focus, the hypocenter had always been inside the earth, right? That's how the earthquakes happen. But in this particular case, the source, as I said, is anthropogenic. The source is manual. Okay, so here is a place where you have made a blast. Maybe you have blasted a dynamite, okay, at this point. And then because you have made that blast, so you have made an elastic collision, and then the elastic waves are propagating, right? So these are the wavefronts, okay? These are the wavefronts. No problem. And then, to make our life easier, we actually conceive the idea of ray paths. So these black lines are your ray paths, right? So you know that at a particular place, the ray paths are perpendicular to the wavefront, right? And then you see this ray is going, this medium is having, this is a single medium, right? So, and then, so this is medium 1 and then the medium 2. So these are two geological rock layers, okay? Layer 1, layer 2, and layer 3. And these 3 layers now are distinguished by their acoustic impedance, okay? And acoustic impedance means is a product of rho and V. Rho means is the density of that layer, and V is the velocity of the elastic wave that is propagating through it. Okay, so suppose the acoustic impedance of the bright yellow layer is rho1 V1, which is different than the acoustic impedance of the second layer, which is rho2 V2, and which is different from the acoustic impedance of the third layer, which is rho3 V3, right? So if the acoustic impedances are different between layers, okay, acoustic impedance, as I said, is the product between density and the velocity of the elastic wave. Okay, so what would happen? This elastic wave will essentially reflect, okay? And then some part of the elastic wave again propagates through the second layer, and then it again hits the boundary between layer 2 and layer 3, and then it reflects again. Okay, and so on and so forth. Then some part of the energy is transmitted, right? So some part is transmitted, some part is reflected. Okay. Now, what you can do, you can actually, like you have put a source here, okay, a dynamite blast, or like a big hammer, you have put a geophone. Okay, sorry, you have put a hammer and you are kind of hammering that area. Okay, big hammers. I'll show you some photographs, and then at some distance, maybe you have put your detectors. Okay, the geophones, which are actually listening to this sound. Okay, and then you listen to the sound. So, for example, this after the blast, you know, maybe at a distance of some 500 meters or so, your first geophone is placed, and after 0.4 second, okay, you hear the sound. Okay, you hear the sound of this reflected wave. Okay, so this 0.4 second is called two-way time, or TWT. Two-way time. Why? Because the elastic wave actually uh, originated or started its journey from here, and then it got reflected here, and then it come back to the detector, right? So it's one way and the second way. Okay, one way and the second way. Hence, this is called two-way time. That means this elastic wave took a time of 0.4 second to take a journey from the source to the receiver, okay, through this media, okay, being reflected at the interface of layer 1 and layer 2, which is having a difference in acoustic impedance. Okay, and then suppose similarly at detector 2, it is recording the reflection from the second interface, okay, and that is received after 0.8 second. Of course, this is also two-way time, and you can see for the second case, of course, the ray path is longer, right? Hence, the time will be different. Although the velocity is slightly different between the yellow layer and I don't know what do we call this color, pink layer. So the yellow layer, between the yellow layer and pink layer, there is a difference in velocity. There is difference in rho as well, which is the density. But the moral of the story that although there is difference in velocity, the ray path is also different. So this roughly takes. This might not be exactly double. This is for your convenience to understand. That's why it is doubled. But it will be certainly longer than 0.4 second. Okay, is that clear, guys?
Yes, sir. Sir,
So this is
it may be possible that two different layers may have the same acoustic impedance because.
Yeah, then you will not be able to resolve it with seismic. Okay, as simple as that. Say for example, it's very similar to optics. Okay, it's very similar to optics. So say for example, I have a glass. Okay, completely transparent glass, and then I put it inside water. Okay, sometimes you cannot exactly dissolve water from glass, right? It happens. Why?
Yes, sir.
Simply because they have similar refractive index, and your eye is not able to resolve it. You understand my point?
Yes, sir.
So there might be a little bit of difference of the diffractive index, but your eyes are not trained enough to resolve that difference. Similarly, if I don't have enough difference in the acoustic impedance, the seismic method will not be able to resolve it as two layers. As simple as that. Okay?
Yes, sir.
Very good. So now the seismic data. Okay, so now I have, with this simple experiment that we have done, I'm now looking at the seismic data. So I'm looking at device 1, that is the first receptor, or first receiver, and then I'm looking at the second receiver. Okay, so, and then what I'm plotting, so in the x-axis, of course, I have plotted the distance between. So here will be my source, at 0 point will be my source, and then I have maybe at 500 meter I have device 1, and maybe at 1500 meter I have device 2. Okay, so this is the distance from the source. Okay, this is the distance from the source. Now, remember, if the devices are close by to the to the source, and you are only concentrating on the data of the nearby devices. Okay, if the devices are close by to the source, and if you are only concentrating on the nearby devices, that data is called near offset data. Please write down, that data is called near offset data. Similarly, if I am considering the devices which are far from the source, okay, I'm only considering the data which is far from the source. Such data is called far offset data. Okay, so near offset data, far offset data, and if I consider everything, that is what we call as full offset data. That means everything I'm considering. Okay, so near offset data, far offset data, and full offset data. Now let us say device 1 and device 2, I will regard them as both as near offset data. Okay, and in the y-axis, what I have drawn two-way time. Okay, so in the y-axis, I have plotted two-way time. So what is happening at device 1? At device 1, what I am observing is the arrival of the first wave. Okay, arrival of the first wave, the one that is reflected, right? So what I am observing, that there is a positive loop and there is a negative loop. Okay, and this is what we call as a wiggle, a seismic wiggle. Okay, and this is nothing but a graphical representation of the arrival of the wave. Now, you remember when we talked about the arrival of the wave, say for example, for P wave arrival, okay, for P wave, what we have seen, that there is a compression and there is a relaxation, right? A compression and a relaxation. Let us say the compression is represented by the positive amplitude. Let us say that is positive amplitude, and this is the negative amplitude. Okay, so now if I draw a bigger amplitude, that means I have a longer compression. Okay, if I have a bigger amplitude, that means I have a longer compression. If I have a smaller amplitude, that means I have a smaller compression. And similarly, the negative part is the relaxation. Similarly, if I think about the shear wave, instead of P wave, let us think that the wave that has transmitted is shear wave. Similarly, we can say maybe which is so we have drawn this sine curve which is above. I am assigning them as positive, which is below, I am assigning them as negative. So it's all it's all about the what is that called, convention, right? So similarly, so I will have a positive part of the wave, and then I will have a negative part of the wave. Okay, and this is what we call a wiggle. This is called a seismic wiggle. Okay? Now, the amplitude, as I said, is directly proportional to the compression or the relaxation. Okay, and of course, and this will happen at 0.4 second, right? Because the two-way time at device 1 was 0.4 second. Now, this juncture between the positive and negative amplitude, this is what we call as the zero crossing. Remember, the juncture between the positive and negative is called zero crossing. Okay. Listen to these lectures very carefully. You will not find these things very well elaborated in Laude's book or any other book for that matter, simply because these are practical stuff. You have to be on the field doing some seismic stuff to actually have a to be able to explain things in a simpler way. So I was fortunate enough to be associated with such practices during my time with Shell. So hence I can talk about these things with a I think simplistic manner. But then if you read any book, things are fairly complicated. Okay, so try to be as attentive as possible. And remember, the seismic is the most important geophysical technique which is practiced in the industry. Okay, so if you wish to have a career in geoscience in the industry, okay, seismic will be the thing for you. I mean, for 90% of the geophysicists work on seismic. Okay, so make sure that you understand what I am talking about. Okay, so it's all conceptual, and try to pay as much attention as possible. Okay, now Similarly, I will find the two-way time at 0.8 second for device 2, and this will have a positive, a negative, and a zero crossing. Is that clear, guys? Everyone? So far, so good?
Yes, sir. Yes, sir.
Excellent. So now, as I said, so first step of this whole business is about seismic acquisition. So seismic acquisition can be of two types. One we call as the 2D seismic, and the other one we call as the 3D seismic. So 2D seismic means, let me just draw a few things for you. Suppose this is the area I'm trying to, this is my area, this is my prospect, okay, where I'm trying to do my seismic survey, okay. So what I'm doing, so I'm selecting some lines. These will be straight lines, huh? Straight lines, huh? So line 1, line 2, at regular intervals, line 3, line 4. And then similarly, I will choose some lines here as well. Line 1, line 2, line 3, line 8. Now suppose I will have my source here. These are my sources, okay? I'll have my source here, and then I will have my detectors maybe here. Maybe at regular intervals, the detectors are placed. Okay. So the same thing will be for this line too. And so similarly, so at each line I will have a set of sources and detectors, right? And so what I will be able to do, I will be able to have a 2D image along this line. I will be able to have a 2D image along this line, this line, and all the perpendicular lines too. Okay, so here I will have my data. So now if I take one such line, okay, and see the section, okay. So if I take one such line, and maybe this is a seismic section, I'll explain how it will come later on. But then if I take this line and look at it, okay, that is my 2D seismic. Okay, one single line, I look at it, it's my 2D seismic. Okay, but what I can do, also maybe I can actually increase the number of lines. Okay, maybe I will increase the number of lines manifold. Okay, both horizon, both east west and north south. Manifolds, you get my idea, and that is done everywhere, huh? So now you see I have a lot more denser 2D lines in the in the whole area, right? Now what I can do, I can ask the computer that I have data at this point, but I don't have data here. So I can to interpolate this whole 2D seismic area. I can ask the computer to interpolate it, yeah, and then I can come up with a 3D volume of seismic data. Okay, I can come up with a 3D volume of seismic data. So ideally, we are still shooting 2D seismic, but at a very close intervals. Okay, and then I'm asking the computer to interpolate the area in between. Okay, so what it means, suppose I have for one data point I have 2, for this third data point I have 6. So I don't know about the data point in between. What I can do, maybe I can average out for the value of the second data point. Okay, understand my point? This is how interpolation goes, and the data becomes the result becomes more robust if I have more number of 2D lines. So if I put more number of 2D lines, I will have a better result. So the more sugar you put to your drink, it becomes more sweeter. As simple as that. So the number of data points you increase in your input, the output will be way more robust. Okay. So the difference between 2D and 3D seismic is simple, that the acquisition is still as 2D lines, but in case of 3D seismic, what is generally done, that all these 2D lines are used to interpolate the area in between. Okay, this is what we call as 3D seismic. Okay, is that clear, guys? The difference between 2D and 3D seismic?
Yes, sir.
Very good, very good. Now there is also something called 4D seismic. Okay, remember that 4D seismic, you might hear about it. I'll just tell you what it is. 4D seismic is, suppose that I have shot a 3D seismic in this area, Bhopal, okay, today, okay, and then from today I start my oil and gas production. Okay, so I am taking out the oil and gas from the underneath, okay, from the subsurface. I am taking it out, and maybe I produce for 20 years. Okay, I have created some fluid disbalance underneath. Okay, some fluids have been replaced from outside, from the subsurface. Okay, so after 20 years, maybe I shot another 3D seismic in this area. Okay, and then I compare these two 3D volumes. I compare these two 3D seismic in front of me. Okay, one 3D seismic is shot at 2020, 2021. The other one is shot at 2041. Okay, so the seismic will reflect the imbalance in fluid. Okay, we will see why later on, because the presence of fluid inside the presence of fluid in the layer changes the acoustic impedance. It changes the acoustic impedance. So because of the simple fact that while we derived the equation for P wave and shear wave, it has it depends on the bulk and shear modulus of the media, right? So as we introduce fluid in the system, okay, the bulk and shear modulus also changes. So remove fluid out of it, the acoustic impedance, the velocity will change. Okay? The velocity with which P and S wave will propagate through the media will change. Okay, as a result, the acoustic impedance also changes, and because the acoustic impedance changes, my seismic output also changes, right? So I can understand the effect of the fluid. I can understand the effect of the removal of the fluid by studying 3D seismics taken at 2 time intervals. Okay, and such process is called 4D seismic. Is that clear, guys?
Yes, sir.
Very good. So we now know about 2D seismic, or we now know about 3D seismic. We also know about 4D seismic. Okay. So 3D survey is designed based on imaging objective. Okay. So it depends on how much area you want to image, the target depth. What is the depth that you want to image very well? The depths of the beds, why we will understand later on. Velocity, size, thickness of the bodies to be imaged. Survey parameters like survey area, fold, I have not explained. I have explained offset, sampling and shooting directions, etc. And balance between data quality and dollars. Okay, this is very important in oil and gas business. Dollar, the money, you are not doing it for fun. You want to make money from it. Okay, so if you invest more in seismic acquisition, your data quality will be better. Now maybe for your purpose, the best data quality is not necessary. Okay, then would you invest as much as money? I mean, simply because the data quality will improve? No, right? So you have to kind of optimize the cost with quality. That I am going to invest such and such $1 million, okay, to acquire my seismic. Okay, and this is the data quality which is expected, and I'll be able to live with this data quality, and that would solve my purpose very well. Okay, so the data quality is directly proportional to the money invested, because the more seismic data you actually acquire, better resolution you get. As simple as that. Okay, so let me also tell you, the lowest resolution that you get from seismic is around 20 meters. Okay, so 20 meters means anything which is closer than 20 meters cannot be resolved through seismic. Okay, now you can see here two pictures of land operations and sea operations, marine operation. You have already seen about marine operation. So air guns, in case of marine, air guns are actually fitted in this particular boat. Okay, and these are called seismic vessels. Remember, these are called seismic vessels, and you can get a job at a seismic vessels. They pay very well. It's very well paying job, and you can be there for 20 days and then 20 days leave. 20 days leave, you come back home and spend life with your family, no work. Then again go back after 20 days, acquire some seismic, and then come back again for 20 days. They pay very handsomely, especially in the Middle East, very well. So what happens in marine operations, of course, that air guns generate disturbances, the acoustic collision that we have talked about, which are attached to these boats, and then you have these hydrophones which are attached to these streamlines. Okay, now what happens, this particular boat actually makes a grid-like movement. Okay, so the picture that I have just drawn, so the boat will start from here, this will go like this, and then go like this, and go like this, and while going it is shooting seismic and detecting data. Okay, and like that he will complete this whole area. Okay, maybe first east west, and then they will go like this, north south. Okay, now whether they will go east west or northeast southwest or northwest southeast, that depends on the geology of the area. Okay, in which area that the which way the beds are dipping and everything. Okay, now parallel to the strike direction, parallel to the strike of the beds, the seismic that is shot is called inlines. So these will be called inlines, which are parallel to the strike of the beds. Okay, and then there will be the perpendicular ones, are generally called cross lines. Okay, they're called cross lines. Cross lines, just cross lines, inlines and cross lines. Okay, so this is how it is done for a boat. This is done for marine operation. Okay, this boat essentially moves around in that area. So marine acquisition is rather simple. It's not very expensive. You can short seismic through marine operations very easily. The land operation is, however, a bit more difficult, because what happens, you see these big trucks, and these trucks generally have vibrators, and vibrators are these big large hammers, as you can see here. So what happens, this hammer actually pounds down the ground. Okay, it's like tons of weight. So when it pounds down the ground, what happens, it creates elastic collision. Okay, so the one of the ways of creating elastic collision, that you dig a small hole and you put some dynamite and you blast it, that creates elastic collision too, but then it is a little bit dangerous, as you know, and not very environment friendly as well. So nowadays more people are going towards these vibrators, okay, which are with large hammers, and very large pounding takes place, and then the seismometers are actually placed at different areas. Okay, and the geophones, which are seismometers, nothing but seismometers, they are the geophones that detect these motions. Okay, now you can imagine this is a flat area. Maybe this is easier. So if I have an area which is mountainous, moving this truck can be very difficult, because you don't only want to get the data along the roads, right? You want to get the data around as well, because it's not necessary that the oil and gas will sit beneath the road, right? So you want to do the operations everywhere. So if the If the land is not flat, if there are such uneven topography, it becomes very difficult to shoot land seismic. Okay, and hence land seismic is rather expensive as well. All right. As we have discussed, that we have near offset data and far offset data. Near offset means the data which is actually from the detectors which are close by, and far offset are the data which are from a distance. Okay. Now you see what we have done. If I go back to this picture, what we have done, if I actually, you can think of that, if I have like hundreds of receivers along a source, and if I put all these seismic wiggles together, this is that we will generate. This sort of pictures we will generate. You can imagine. Okay. And this is what we call as an unprocessed image. This is what we call as an unprocessed image. Unprocessed means this is not processed at all. This will not give you enough geological information. This is just the set of wiggles that you have received from your seismic shooting. Okay. So now what you have to do, you have to take this particular data which you have just acquired by seismic through a set of processing parameters or processing steps to get the picture of that makes geological sense. So this is the field recorded version of the data, and then it goes through data processing stream, and finally you come up with a subsurface image. Now here you can see I have beautiful layers. You can see beautiful layers, and you can see something has happened here. These beautiful layers are kind of truncated against this reflector. Can you tell me what this could be? Anyone? This layer, you can see these layers are fairly horizontal, and all on a sudden I see, you can observe this, right? You can understand this, that there is like a break. Something is changing along here. What this could be? Can someone tell me geologically?
Faults?
Are the faults horizontal generally? This is a fault. You can see that this reflector is displaced somewhere here. If you match the quality, this area is kind of gone down here. So this is a fault. You are right, but what is this? What are the horizontal breaks that you find in a geological succession?
Unconformity.
Exactly. So this is an unconformity. Absolutely right. This is an unconformity. What sort of unconformity is this? Can you tell me? Angular, disconformity, or non-conformity? How is it? So the attitudes of the bed above and below the unconformity are different. So what type of unconformity is this? Angular unconformity, right? This is an angular unconformity. You can see that these beds are kind of truncated against this bed, right? So this is an angular unconformity. You read about angular unconformity, disconformity, non-conformity, or not?
Yes, sir.
Yes, sir, we have.
Yeah.
Okay. So are you convinced that this is an angular unconformity or not?
Yes, sir.
All right, good. If you don't agree with me, you should argue with me as well, huh? Please. Are you convinced that this is a fault?
Yes, sir.
Simply because you see, this seismic, this particular layer, okay, is this particular layer. From the seismic character you can make, right? So there is some sort of displacement. So this layer was here. Okay. So what sort of fault is this? Normal fault, thrust, or reverse fault? Hmm? Tell
Is
me.
it a normal fault?
It's a normal fault because the hanging wall is moving down, right? This is the hanging wall, this is the foot wall, right? The
Yes, sir.
hanging wall is moving down. So it's a
Yeah.
normal fault. Okay, so you have a normal fault, you have a little bit of folding as well, as you can see here. Can you see that? Not very strong, but there is a little bit of folding,
Yes, sir.
right? And then there is a fault, and then there is this beautiful unconformity, right? So this is the unprocessed data, and through data processing, we are about to give rise to something which is more geological looking. Okay, and let us see how it is done. Now, let us again look at how the seismic acquisition is being taken place. So you have source, and then you have a series of receivers. Receiver 1, 2, 3, 4, 5. Okay. Now you see, if I make a elastic wave at S1, what would happen? Of course, the layers will be reflected. Okay. So I am now considering only the interface between 2 and 3. Okay. So I am now not considering the interface between 1 and 2, but you can imagine that the thing will be the same. Okay. Now let us consider the interface between 2 and 3. Okay. Now what I am observing that if I create a blast as S1, there will be some waves which are directly reaching to R1, R2, R3, R4, R5, okay, which will not be transmitted through the media, okay, which will not be kind of reflected through the layers, okay. They will be directly arriving, right? You agree with my point? Yeah.
Yes, sir.
Just simply directly arriving. So, and at R2, R3, R4, R5, okay, I will find the first batch of wiggles. Of course, the timing of arrival will be more if I am moving from near to the far offset. Okay, this is two-way time and this is offset distance, so will be more. And this is what I will observe. Now, this is not exactly two-way time simply because this is the direct arrival. Now, this direct arrival of waves is not of much of our interest, okay? Because this is not being reflected. So the very first set of waves that I find from my seismic sections are generally removed from the seismic section because they do not tell us anything about the reflection, okay? So what I can do, I can remove them, okay? I can get rid of them from my seismic section. This is the first step of processing, that you get rid of the direct arrivals, because direct arrivals are not giving you any useful information about the subsurface. Okay. Now, of course, what has happened that the seismic wave which is generated at S1 has reflected here, has come back to R1, and so I get, due to the reflection between 2 and 3, I get a series of wiggles. Okay, I get a series of wiggles at R1, R2, R3, and then if I put kind of side by side of them, what I will observe that there is this set of reflectors. Now, if I simply join them, I can see that there is although the bed is horizontal, that the reflection is coming to be inclined. Do you agree? So the bed is horizontal, the interface is horizontal in this particular example, but because of course the two-way times are getting higher as I am moving from the near to far offset, I am observing that there is like a inclination in my data. Okay, if I try to join them together. Yeah, so far so good.
Sir, how are we distinguishing that R1 receives the wave from direct or from the reflection?
No, of course, the if I just look at R1, okay, what I will observe that the two-way time, the time at which the direct arrival comes will be the first. So the first set of data the first set of wiggles that I am observing in my receivers are removed.
Okay.
Is that right or not? You understand?
Yes, sir. Yes, sir.
Because they will be shorter, of course. I mean, if I consider the interface between 1 and 2 even, the amount of time taken for that two-way time will be higher than the direct arrival. Right?
Yes, sir.
So the first arrival I actually can remove from the data. So the reflection between 2 and 3 will be put like this. Then similarly, the reflection between 1 and 2 will be maybe somewhere here. You understand? And the reflection between water and 1 will be somewhere here. Okay. But because as the layers are horizontal, you will find these to be also like parallel to each other. Okay, although they will be inclined. Inclined simply because the two-way times are increasing from near offset to far offset. Is that clear so far? Tell me.
Yes, sir.
Excellent. So here we go. So I have removed now the top, the direct wave. Now let us say I have this point A, okay, and if I now design my experiment in such a way that I have a series of source and receivers, okay, a series of source and receivers, okay, which are exactly trying to image point A. And this point A is called common midpoint. So now what I have done, I have pair of source receiver, pair of source receiver, pair of source receiver put like this, and I am trying to image this point A. And this is point A is called common midpoint. Okay. Now you see, please don't be confused with the earlier picture. I am actually trying to image different points. I am trying to image different points along this reflector. Reflector means the interface between two layers of different acoustic impedances. Okay, so here I'm trying to, here all these points are different. Okay, now if I'm looking at this particular point, okay, this particular point, and then I'm doing this experiment, okay, and I'm trying to image that same point with a set of source and receivers, I will also generate something like this. Okay. So what is this doing? This is actually trying to amplify the data. So if I am simply using one source and receiver, the data that I am receiving, that might not be strong enough. That might be full of noise. Okay. But instead of use to image one single point, several source and receiver pairs, what I will be able to do, I will be able to create a strong. Okay, although because the two-way times are different, they will have its inclination, but I can remove that inclination. I can remove that curvature. I can remove this curvature using the actual velocity. Okay, use the actual velocity, and if I use the proper velocity, what I can do, I can use these common midpoint gathers. These are called common midpoint gathers. Okay, I can use this a particular velocity and I can make this flat. Okay, I can make this flat. Now remember they are representing the same point. So what I will do, I will put all these traces together. I'll ask them to be coming together because they are representing the same point. And then I will finally find a wiggle which is of 10-fold. So this is what we call as fold. So single fold. This is a single fold image for this point, say this point A. Okay. This is a 1, 2, 5-fold image of point A. Okay. I can even create a 10-fold image of point A because, and then what I'm doing by doing this correction of with the actual velocity, I can put them flat and then I can stack them together, and this process is called stacking. Okay, what this does, that the signal becomes stronger, okay, and noises become actually reduced, okay, and I come up with a beautiful stacked trace, okay, and this stacked trace, think of that at this point what I'm having is a series of stacked traces. Okay, I'm having a series of stacked traces. Okay, now after I am getting of stacked traces, okay, and you know this series of stacked traces are also again also what is that called, are inclined. Now what we have to do, we have to, from that inclined reflector, we have to make it to a horizontal reflector or the reflector of the actual dip, and that is done by a process called migration. Okay, we will talk about migration and continue with this seismic in tomorrow's class. Okay, unless you have a, please ask if you have a question, anything you have not understood. Yes, you have a class tomorrow because yesterday we had a pre-recorded lecture. So you will have a class tomorrow. I wanted, because the thing that I taught in the last class was simpler. So it could have been done by a pre-recorded lecture, but this part you need to have this interaction, you know. Otherwise your doubts will not be cleared. I will keep on speaking in a pre-recorded lecture, and if there you need a clarification, you will not be able to ask at that point in time, and you will miss out. So hence I wanted to design these lectures for this week so that the harder part or the more complicated part are through direct lectures. Is that fine with you guys? You are coming tomorrow. What do you mean? Okay, you are coming back to the campus tomorrow.
Yeah, maybe some of the students will be traveling.
How many of you are coming back? Can you tell me?